So there's two parts to the fundamental theorem of calculus, and they go hand in hand. So we're going to sort of talk about them together. The first part of the fundamental theorem of calculus just says that derivatives and integrals are opposite operations of each other. So that if you take the integral of a function and then take the derivative of that, you should end up with the function that you started with. So they're just opposite operations. And we know that this little symbol, right, is our integral sign. So if we take the derivative of the integral of a function, we just get that same function. We're going to come back to that in a second. The second part of the fundamental theorem of calculus says that if I try to take the integral of a function from a to b, there is some other function, capital F, where capital F is a function that represents the area under the curve little f of x. Okay. So capital F, or the antiderivative, so before, when we found these antiderivatives or these integrals, we were looking for area under a curve and we were evaluating them at specific numbers. Well, for almost every function that exists, there is the integral of that, which is a function. And so we can write the integral of something as a function in a functional notation. So for example, if
Mr. Bachelor, I don't think we can hear you. There might be an issue with your microphone.
All right, can you guys hear that again or no?
Yeah, we can hear you now.
Yeah, we can hear you.
All right. Everyone's good? You can all hear me?
Yes.
All right, perfect. So where was I when my audio started cutting out?
Oh, like right at the beginning of the next slide, I think.
Did you guys hear all the part about the second part of the fundamental theorem right here, where we were talking about capital F being an antiderivative of little f?
Yes.
Yeah, no?
Yes, we heard that part.
Okay, you guys are all able to hear this part? Okay. Just cut out right here?
Yes.
Perfect, okay. So we're gonna make an example of a simple function here with little f of x equal to 1. So we should be able to figure out what the integral of that is. The integral of little f of x equal to 1 should just be capital F of x is equal to 1. should just be x, or at least x is one function that could be an antiderivative of 1. The reason is, if we take the derivative of capital F of x, we have to get little f of x. Everybody follow with that? And one function that when we take its derivative gives us 1 is just x, the function x. Everybody okay with that or no?
Wait, could you explain that again?
You all can still hear me, right? Nobody's responding, so that's why I'm not sure if you guys are understanding or not understanding.
Someone just asked a question.
Can you hear us?
You guys are talking?
Yeah, wait.
Yeah, I can't hear you guys at all. Cool.
That's unfortunate.
So what we did here was I just picked some simple function. Little f of x is equal to 1. And I said, what's the integral of that? What's the antiderivative? What's a function that represents the area underneath this curve, f of x equals 1? And the answer is x, because if I take the derivative of x, well, then I get 1. Right? And that's the first part of the fundamental theorem of calculus, is that the derivative of the integral should just be the function. And so here, if I take the derivative of this thing that I'm claiming is the integral, I should just get my function. I should just get 1. And so most functions, not all, but most functions have an explicitly defined integral that is also a function. So for example, for f of x equals 1, one of the integrals of it is x. There's lots of them. We could say x plus 1 would also work, wouldn't it? Because if I take the derivative of that, what do I get? I get 1. Right? It could also be x plus 2. If I take the derivative of that, I get 1. It could be x plus any constant, right? Because if I take the derivative of that, I get 1. And so there are functions that represent the area underneath the curve of most other functions. So for example, if I said, little f of x was equal to x, what would capital F of x be? What's a function that when you take its derivative gives you x?
X squared over 2?
Exactly, right? If I take the derivative of x squared over 2, that just gives me x, right? This is the integral, or the antiderivative of x. It's a function that when we evaluate it in this way, if there were limits on it, would give me the area underneath the curve f of x equals x. So using that information that we have, we could say that the integral from, let's say, 0 to 3 of 1 dx, what's the antiderivative of 1, or what is 1 antiderivative of 1? It is, we said earlier that it was x, right? So we're going to take x and we're going to evaluate it at 3. And we're going to subtract from that x evaluated at 0. And what does that give us? It gives us 3 minus 0, or 3. And we know that if I had the curve f of x equals 1, right, that just looks like this. If I were to look for the area underneath the curve from 0 to 3, what should that area be? It should be 3 units, and that's what we get. So that's how this second part of the fundamental theorem of calculus works. Find the function that is the antiderivative of your function and evaluate it at the upper limit, evaluate it at the lower limit, and subtract them. Does that make sense to everybody?
Yeah.
All right, cool. So we're going to use that in addition to this, that the derivative and the antiderivative are inverse operations of each other when we go from a constant to x, to be able to evaluate some other functions like these, which we'll do in just a second. Before we do that, let's think about the derivative with respect to x of the integral from something like 0 to x of x. Or actually, we're going to use a different variable here. We're going to just say t dt. So we know what the integral of the function t is, right? We found that a minute ago, didn't we? Just like we found the integral of the function x. What's the integral of the function t? It ought to be t squared over 2. So this ought to be the derivative with respect to x of t squared over 2, going from 0 to x. And so this ought to be the derivative with respect to x of x squared over 2 minus 0 squared over 2. And the 0 squared over 2 goes away, and this just becomes the derivative with respect to x of x squared over 2, which is just x. Right? We just take this x and plug it in for the t. That's effectively what we've done. We see basically how this works?
Yeah.
Okay. Let's try to do it with slightly more complicated functions that have maybe less pleasant constants. Do we need to know what function is the antiderivative of cosine in order to be able to do this? The answer is no, but we can use it if we know what it is. So does anybody know what the antiderivative of cosine is, or what the integral of cosine is?
Sine.
It should be sine, right? We could say that sine of t is, it's an antiderivative of it. It's not the only antiderivative of it. Because I could also have said sine t plus 5 or sine t minus pi, because both of those, any of those functions, when you take their derivative, just get you back to cosine t. So since we know that sine is an antiderivative of cosine, we could rewrite this as a derivative of the sine of the upper limit minus the sine of the lower limit. And that's the second part of the fundamental theorem of calculus, right? If we know the antiderivative, plug in the upper limit, plug in the lower limit, and evaluate. But now, rather than just evaluating this all together right away, we need to take the derivative of it. So what's the derivative of sine x? It's
Cosine x.
Cosine x. And what is negative sine of negative pi? It's all just a constant, right? And so if we take the derivative of a constant, what do we end up with?
0.
0, or just cosine x. And so we chose one specific antiderivative of cosine t and used that. What if I'd chosen a different one? What if I'd said, well, couldn't sine t plus 8 also be an antiderivative of cosine of t?
Yeah.
Yes.
Right? Because if I take the derivative of sine of t plus 8, I still just get cosine of t. So if we'd done it that way, we would have ended up with the sine of x plus 8 minus the sine of negative pi plus 8. And the sine of x's derivative would have still been cosine x. And the 8 is just a constant. And besides that, it cancels out with this -8. And this is still just a constant. We would still just end up with cosine x. So you can choose any antiderivative, but we usually choose the simplest one that doesn't have extra constants added into it. Good or no? And so we'll note, hopefully, that anytime this lower limit is a constant and the upper limit is just x or just some variable, that the derivative of that antiderivative should just be the original function in terms of whatever variable is in the upper limit, right? Because the constant that's in the lower limit, when you retake the derivative, just goes away and becomes 0. Everybody good there or no? All right. I don't know if you guys are saying anything, but if you are, I can't hear you anymore.
No one said anything.
No one said anything. Okay. Is everybody all right or no? Question?
So because there's a variable for the top part of the domain, or not the domain, but just the
upper limit,
whatever you're taking the integral at, does that mean like it's the area for the function from negative pi to like infinity?
It's not to infinity. Basically, it's saying from negative pi to any x value we choose.
All right.
Yeah. So if I wanted to find the area underneath cosine of t from negative pi to any x value, I could use this formula without the derivative part.
X after.
Right. You plug in any number x. It might be pi. It might be 17. It might be 3000 e. Who knows what it is? But you could plug that in and find the area underneath the curve from negative pi to that value. Correct.
All right.
And we're going to start doing that tomorrow a lot. But right now we're just kind of trying to figure out how all these things are sort of intertwined. And the AP test always has a question or two similar to these, so I think it's important for us to go through them.
Is there a reason sometimes we do like this method and then sometimes we'll do like summation?
Okay, so this is a little bit different than the summation. So the summation that we were doing is to find the specific area underneath the curve or to find the actual value of the integral. What we're really looking at here is it's the whole idea behind what an integral is and where it comes from and how the derivative and the integral are inverse operations of each other and cancel out, right? Because there was no derivative in front of our integrals when we were evaluating them before with the limit and the summation. This is different because it's got a derivative in front of it. And to be perfectly honest, I wouldn't spend as much time as I am on this if they didn't always show up on the AP test, because this isn't like, it's not something that's super functional for you guys to use in any real problems that we'll do, other than the AP test is going to ask about it. So we have to do it. Yeah, Claire, basically we're just proving that we're basically just showing that they are inverses of each other when the lower limit is a constant and when the upper limit is just a variable. That's the whole purpose of what we're doing at the moment. What do you mean? Can we use these to evaluate? Oh, so I see what you're saying. I think, yeah. So like, since we know that the antiderivative of cosine is sine, can you just use that to evaluate rather than doing the summation and the limit? Is that what you mean? Yeah. Yes. And that's exactly what we're going to start doing on Tuesday, is figuring out how to do that. But then there won't be these derivative pieces attached to it. The derivative pieces are only attached to it for us to show that we know that these are inverses of each other. And really, they're only there because the College Board wants to make things a little bit more complicated for you. Like, there's no real reason for us to be doing so much work with this, other than you need to get the questions right on the AP test. I mean, it's not This is not something that's usually covered as in depth in a regular calculus course. If I was just teaching a calculus course that wasn't geared towards the AP test, I would be like, all right, the derivative and the antiderivative are inverses of each other, and this is how you find them, and we do it. And we wouldn't have to do all this technical junk, but that's the way it is. So let's look at the next one. You may or may not recognize what the antiderivative of this is. You should know a function whose derivative is 1 over 1 plus t squared, but it doesn't matter if we know that function or we don't. Eventually, you're going to want to know that function. It's the inverse tangent function, right? But if we don't know that right now, we could just make some statement like, let capital F be an antiderivative of 1 over 1 plus t squared. And so the antiderivative from 0 to x would just be capital F of x minus capital F of 0. And what's the derivative of the antiderivative? Well, it's just the function in terms of x. And the derivative of the constant, capital F of 0, is just 0. And so we just end up with our original function. Does that make sense to everybody or no? Everyone all right or no?
Wait, so when you evaluate the whole derivative of the integral thing and the thing that comes out at the end, so like cosine x or 1 over 1 plus x squared, is that the value of the integral or is that the function?
No, that is the value of the derivative of the integral of this function from 0 to x. It's just that function in terms of x. That's all it is. It doesn't represent anything other than the fact that the derivative and the antiderivative are inverse operations of each other. It doesn't represent the area underneath the curve. It doesn't represent anything other than us
so it doesn't
showing and knowing that those are inverse operations. Does that help make sense now?
Yeah, so it doesn't actually mean anything besides what we're trying to prove.
Correct. All right. So we're going to look at a couple more of these that are slightly different. And what's different about these two? We're still finding a derivative, and it's still a derivative of an integral of some function. But what's different now?
The x is squared in the integral.
Right. So rather than us just having a single variable up there, we have a function. We have an x squared. And so we know, again, what's the integral of cosine? We already figured that one out, right? What's the integral of cosine? What function has a derivative that equals cosine? Ought to be sine, right? And so the second part of the fundamental theorem of calculus says sine of x squared minus sine of 1 is what we're going to take the derivative of. So sine of 1 is just a number. It's just a constant. So when I take its derivative, it's 0. But how do I take the derivative of the sine of x squared? I have to use chain rule, right? So the derivative of sine of x squared is cosine of x squared times the derivative of x squared. So 2x cosine x squared. So this fundamental theorem of calculus thing, where the derivative and the antiderivative are inverse operations of each other, is only true if we're going from a constant to x. If we're going from a constant to some function, we have to take the derivative of that function and multiply it in using the chain rule. Good or no?
Makes sense.
All right. So using that same logic, let's do this bottom one. You probably don't know what the integral of e to the t squared is. So we're just going to let capital F be an antiderivative of e to the t squared. And so now we're looking for the derivative with respect to x of capital F of x squared minus capital F of 0. And no matter what this capital F function actually is, when I evaluate it at 0, I just get a number. And when I take the derivative of that constant, it's just 0. So all I have left is the derivative of capital F of x squared. Well, that ought to be the derivative of capital F evaluated at x squared. So what's the derivative of capital F? Well, it's e to the t squared. So this ought to be e to the t squared, right? Because our upper limit is x squared, times the derivative of the x squared. Good or no? Everybody all right or no?
Yeah, that makes sense.
We're going to pull this page up here. Actually, yeah, we'll keep it down there. All right, let's look at this one. How's this one different?
X is the lower limit?
Right, our x is in the lower limit rather than in the upper limit now. And so we can use the same kind of process. We can call capital F an antiderivative of 3t sine t. And so what we're doing is taking the derivative of capital F of 5 minus capital F of x. And so the capital F of 5 becomes 0, but our derivative now becomes negative. And then the derivative of capital F at x is just this function, 3t sine t, evaluated at x. Does that make sense to everybody? Anybody have any questions on that? Everybody good with that?
Yeah, that makes sense.
Okay. And in a second, we're going to talk about a rule. In fact, we'll talk about it right now. Right now. Now is good. We have this rule right here, which I'm going to come back to this page in a second, that says you can also take an integral from a to b of a function, and you can flip the limits of integration and make it negative. So we'll come back to that rule in a bit, but we could have done that here. We could have flipped the limits of integration, made it 5 to x, and just made it a negative, and that would have given us the exact same thing. So hopefully you guys see that that would have worked out the same. Yeah, I hope so. All right, let's take a look at this one. The integral from 2x to x squared of 1 over 2 plus e to the t. So now we've got an issue where the lower limit and the upper limit are both different functions. So we can still let some function capital F that look like an F? There we go. Big red F, just like your grade in this class. So we're gonna let F be an antiderivative of 1 over 2 plus e to the t. And so this effectively just becomes a derivative of capital F of x squared minus capital F of 2x. And the derivative of capital F of x squared is 2x times 1 over 2 plus e to the x squared. And then this one becomes 2 times 1 over 2 plus e to the 2x. Good or no? You can put the 2x and the 2 in the numerators up there if you want. But everybody okay with that or no? You guys are awfully quiet today. It's concerning. Are we good or no? All right. All right, now we've got a couple of these rules that I want to talk about. We're going to use. So first, we already talked about this. You can flip the limits of integration and put a negative out in front, and I think we saw why that works out with that previous one we did. But additionally, you can take a constant out of an integral. So if I have a constant times a function like 7x, I can take the 7 out of the integral, just like we did with limits, just like we did with summations, just like we did with derivatives. You can pull that constant out. And then also, if I have one function plus another function, like x squared plus x inside of my integral, I can separate that into two different integrals, x squared and x, and do them separately. And then these last two, besides the one I've starred, are important ones to think about, that an integral from a to a of a function is always 0. Well, an integral, remember, represents the area underneath the curve. So if I go from here to here and don't move, there shouldn't be any area underneath the curve. So if you have an integral from 1,000 to 1,000 of anything, it's always equal to 0. And then the last rule down here, which is another important one, if I have A and I have B and I have C, and I've got some function, the integral from A to B plus the integral from B to C ought to equal the integral from A to C. And likewise, if I knew the integral from A to C and the integral from B to C, I could do A to C minus B to C, and that would give me A to B. Does that make sense?
Yeah.
Cool. All right. Last thing we're going to do today then is we're going to answer these 5 quick questions using those integral rules that we just looked at. And then you're going to have an assignment on the fundamental theorem of calculus plus an assignment on this tonight. And after that, we'll be all ready to really actually start integrating functions for real tomorrow. So first off, what's the integral from 2 to 2 of g of x? Doesn't matter what g of x is, right? If I integrate from 2 to 2, I ought to get 0. Okay. Now, if I have an integral from 5 to 1 of g of x, but I know the integral from 1 to 5, I ought to be able to flip the limits of integration and make it negative. That was that rule that we started on the other page, so that ought to be -8. Everybody good with that?
Yes.
All right. What if I want the integral from 1 to 2 of 3 f of x? Well, that should be the same as 3 times the integral from 1 to 2 of f of x dx, which ought to be 3 times -4 or -12. Everybody good with that one?
Yes.
All right, and what about the last one? or not the last one, the second to last one, from 2 to 5 of f of x. I don't have 2 to 5 up here of f of x, but I do have more than 2 to 5, right? I have an integral from 1 to 5. And what would I need to subtract from that to get just 2 to 5? I'd have to take off the section from 1 to 2, which I also have. Good or no?
Good.
All right. And then our last one here is the integral from 1 to 5 of f minus g. Well, that ought to just be the integral from 1 to 5 of f, 6, minus the integral from 1 to 5 of g, which is 8, or negative 2. Everybody good with those or no? Those ones I think are pretty straightforward.